Every day is a good day for math. That's what I like to hear. What we do now with vectors is we relook at something you did in grade 10, y equals mx plus b. How you do an equation of a line, and we change it to say, could we do the same thing, but consider only vectors instead of y equals mx plus b? And if we can consider it doing it in 2 dimensions using only vectors, and it works, maybe we can apply this same idea to 3 dimensions. And there is no y equals, well, we haven't done any official y equals mx plus b in 3 dimensions just because it gets complicated. So this is going to allow us to do equations of lines in 2 dimensions, but also in 3 dimensions, which is way more helpful because for most things in our real life, if something's traveling in a straight line, now you can use a vector to describe it as opposed to trying to figure out a complicated way using our analytic geometry. So the idea is this. A, B, and C, or A, R, and C, sorry, A, R, and C are all on the same line. And what you could do is if you wanted to go to any point on the line, right? If I wanted to pick any point, say R on this line, I could start at my origin and go to A and then go in the direction of C a certain distance and I would get to R. Right. So OR is equal to OA plus AR. That's our regular vectors. And OR could also be seen as going from OA and then some scalar or some proportion of going from A to C. So what this means is as soon as you have 2 points, because that's all you need to define a line, you can define any point on that line by starting somewhere and going a specific amount in the direction that you need to go. So what we have in our equation of our line is we have a starting point from a position vector and what we call a direction vector, which basically saying A to C is the direction you need to go to be on this line. And does it make sense that A to C would be the same as going from A to O plus O to C? And in position vectors, A to O is negative A, and O to C is C. And again, I like writing it like this way. You'll often see them write it backwards, C minus A, just because they like the negative second. Yes? T is just some number. So for example, here, it looks like about 2/5 of the way to C. If I wanted to get to R, I would go 2/5 of the way to C, and then I would get to R. If it could be any number. If I wanted to get to point M, I would say, oh, I need to go 4/5. It's a nice M. If I would like to go to point N back here, then T would be a negative number because I'd switch directions and go backwards about 1/5 of the way from A to C. So the vector equation of a line, what's really nice about it is that you just need any point, so any position vector A, and then a direction vector B, which is just negative A plus C. And again, maybe I'll write it that way. So as soon as you have 2 points, you can find the direction between those 2 points by using the position vectors, and then you could use any one of those points as a start. Then we say there is some scalar T, some multiple, to get to any point on that line. So now we're going to see how this vector equation can be written in different forms and how it connects to what we already know, which is y equals mx plus b. So we've got a vector equation of our line. We've got a direction vector and a scalar. So the vector equation of line is any vector r can be shown as starting at any vector a and then going some multiple in the direction vector b. This is your vector equation of a line. If you write this as points, okay, then any point on the line x, y will equal a1 and a2, those are the points on A, plus t times b1 and b2. And b1 and b2 would be the direction vector. Probably good to see an actual example of this. But then if you look at the x-coordinates on their own and the y-coordinates on their own, this is called the parametric form. So let's take something that you already know. Let's say we go through the point 0, 2 and 1, 5. There's a straight line. You know that the equation of this line from grade 10 math would be y equals, the slope is over 1 up 3, so it'll be 3x, and your y-intercept is 2. You know that the equation of this line is y equals 3x plus 2. As a vector equation of this line, this point, its position vector is 0, 2. This one, its position vector is 1, 5. If I wanted to find my direction vector b, which would be this, would be my direction vector b, I would have to go negative a to go back to the origin, and then add vector 1, 5, which would give me my direction vector being 1, 3. Notice that my direction vector has an x value of 1, a y value of 3. How that relates to the slope of our line being rise over run, right? When you write slope, you write the y over the x. When you write a direction vector, the x is on the top, the y is on the bottom. So then your equation of your line in vector notation says pick either one of those points. It really doesn't matter which one. Let's say I choose 0, 2 plus something times 1, 3. Can you see that if you put t equals 1, you would get the point 1, 5? If you put t as 2, you would get the point 2, 8, which is another point on this line. If you put t in as a half, you would get 1 half, 3.5, another point on that line. So the vector equation gives you any point on the line without being forced to have, like y equals mx plus b, you're forced to have your y-intercept to use that one, right? So this one doesn't matter what point you have, which makes it a little bit more flexible. Now the parametric equations say that all of my x coordinates are always going to be 0 plus t, or whatever t is. And all of my y coordinates are going to be 2 plus 3t. That's the parametric equation. They look at each coordinate, the x coordinate and the y coordinate separately. This one happens to be very similar to that. That's just by coincidence. Okay? So this is the parametric equations where you look at the individual variables. Then finally, if you take each of those equations and rearrange them to get t by himself, you can then equate the two. Since t is equal to this and t is equal to this, you get the Cartesian form. Now this is the abstract way of doing the Cartesian form. Let's go back to our example to see what does the Cartesian form look here. There, I have t all by itself. This equation, can you see that if you took y, subtracted 2 on both sides, and divided by 3, you would get t? And once you're equal to t on both, you can say, so I know that x has to equal y minus 2 over 3. And now you can simplify and rearrange this. I can multiply both sides by 3, and you will get exactly y equals mx plus b, which is the form you're used to, Cartesian form. So you can take a vector equation and change it back to our Cartesian equation. So a vector equation of a line, which we always use r, not sure why, some point on that line, it goes through the point 2, 5, so there's a starting point, and it's parallel to 3i minus 4j, so that's your direction vector. 3 in the x direction minus 4 in the y direction. And it's very easy to write the vector equation of the line. Once you have the vector equation of the line, you can give the parametric form. Parametric form just says, look at your x coordinate. It's 2 plus 3t. Look at your y coordinate. It's 5 minus 4t. Then to look at your Cartesian form, you solve for t first in both of those equations. So can you see in the first equation, you would get x minus 2 divided by 3? And in the second equation, you would get y minus 5 divided by negative 4? What do we have now? Well, I can equate the two. X minus 2 over 3 is equal to y minus 5 over negative 4. I can multiply both sides by 3, multiply both sides by negative 4 to get rid of the fractions. Now, mathematical controversy. Okay. Some teachers, have you ever heard of cross multiplying? Okay. There are some teachers that will say, I will never use that word. I will never talk about it. Because it's like a shortcut to do something, and therefore it should not be used. I disagree because I think, can you understand that if you multiplied both sides by 3, the 3's would cancel out on this side, and the 3 would move up to this side? And if you multiplied both sides by negative 4, so I feel like if you understand what's happening, I don't mind using cross multiplying at all. If I would teach it to you and say, just use this, doesn't matter how it works, then yeah, absolutely I feel like that would not be a good teaching method. But now, if I multiply this side by negative 4, that would be this, and I multiply this side by 3, that would be this. We can distribute. Negative 4x plus 8 equals 3y minus 15. And if I wanted to, I could rearrange this equation to get y by itself, add 15 to both sides, and dividing by 3, I get negative 4/3 x plus 23 over 3. This is y equals mx plus b. This is not very nice to use if you were graphing. Yes?
If it asks for the Cartesian form, do you want the y equals mx plus b or the x minus a1 over b1?
You could leave it like this. I always like to change it to y equals mx plus b to sort of convert it back to this is what you're used to from grade 10. Okay? Now, if I gave my grade 10 students right now this one to graph, they would all complain. Because it's sort of like, oh, those aren't nice numbers. But you don't, like, yeah, this wouldn't be fun or easy to find a nice number on. The vector equation, oh, we already have a nice number. What does this mean? Go 3 in the x direction, go down 4 in the y direction. Find another nice point. And so the vector equation tends to use nicer points. Y equals mx plus b, because it's so rigid, can sometimes be forced to use not nice points. But can you see that the direction vector here, 3 over negative 4, is related to the slope, negative 4 over 3, in the equation? You need to solve for t in order to get the Cartesian form. Because the Cartesian form says after you've got the t's the same, then you can equate those fractions. So on this one, it's going to take us a little bit of work to get the direction vector, because the direction vector needs to be perpendicular to 3, 1. Okay? What are some things we know about perpendicular and vectors so far? Something's equal to 0. What is equal to 0? Cross products equal to 0 means they're parallel. The dot product equals 0 means that they're, remember? Okay. Oh, that would work so well if it did, but it doesn't. Yeah, if you think that your dot product has cos theta in it, and cos of 90 degrees is 0, means that if your dot product is 0, the angle is 90. So we need to make something, we could think of something as a dot product here to create something that would make it equal to 0. Or we could also use what we know about slopes. If two slopes are perpendicular, what did you do to them? If one of them's 2/5, perpendicular one would be? Flip it. 5/2. Good. Negative 5/2, right? So all we have to do is flip them. And if that one is positive, we need to make this one negative. And you could put the negative with the 1 or with the 3. It really doesn't matter. Now that I put the negative with the 1, can you see that your dot product would be 0? Dot product means multiply corresponding points. Negative 1 and 3. 3 and 1, add them up, you would get 0. So now we have our direction vector. And your equation of your line is always a starting point, which we're told has 2 and 5, plus some multiple of your direction vector, negative 1 and 3. And if you have the equation, the parametric equation is super easy to write. Right? This is just a matter of, can you remember that your parametric is just the x coordinates and your y coordinates separated? For your Cartesian, you first have to solve for t. So in the first one, t would equal 2 minus x. In the second one, t would equal y minus 5 divided by 3. So 2 minus x is equal to y minus 5 divided by 3. Multiply both sides by 3 to get rid of the fraction. And if you wanted to solve for y, it would be really easy. There's your y equals mx plus b. How we did shortcuts? Where?
The cross multiplying. That I've seen teachers that don't do cross multiplying, some that do other shortcuts like that. I learned a lot of different ways to multiply and divide things and stuff. And ensure the real value of the numbers so the kids wouldn't understand. And they made us do math in a bunch of different ways because all of the teachers did it a different way. It's very unhelpful.
Okay. So is this okay, what we've done here?
This is okay.
Okay. Whew. Yes. So if I have a vector that's -1, 3, okay, so that would start here, go 1 back, and then up 3. That's that vector. If, and that one's going to be perpendicular to 3, 1. Now 3, 1, which I'll do here in purple, that would be starting here, would go 3 in this direction, and 1 up. Can you see that that would be perpendicular? It could be +1 and -3. Right? Because if I did +1 and -3, I'll do that in red. Okay? If I made the 1 positive and the 3 negative, that would still be perpendicular there. Mm-hmm. Yes, this question would be identical if you used 1, -3. It would be identical if you decided to use something like a multiple of that. Say I multiply that one by 2. That would also work. 2, -6. See, whenever you change your direction vector, it just means that your t value changes proportionally to find the same points. Right? With this one, if I wanted to go 1 down and 3 up, t would have to be 1. If I had the red one, then t would be -1, would produce the same point. Again, what's really nice about the vector equation of the line is you just need the direction and any point. Whereas y equals mx plus b, you needed the slope and a specific point, the y-intercept. Or you had the point-slope form of the equation. Remember the y minus y1 equals mx minus x1? It just was not as convenient to work with. But the vector equation line really makes it simple. Say, I need any point and the direction. Once I have a point in the direction, I can find anything by just doing some multiple of that direction. Right? This line, I want to walk on this line. I'm starting here. If you want to walk a certain distance, just tell me what distance I need to walk along that. That's the value of t. Oh. Good thing that's not on the video. Whew. So what do we need? We need a point. We have that. We need our direction vector. And our direction vector b will be take one of them and go back to the origin. So if I take A and go back to the origin, can you see that that would be -1, 4? Okay. Again, I find if you want the direction between A and B, it is so easy to see it if you draw a diagram. If I want to go from A to B, I could first go back to O and then go to B. That would give me A to B. Well, A to O is just negative of vector A. Plus now, we're going to go from O to B. Well, that would be plus 5, 8. And we've got our direction vector being 4, 4. Can you see that the direction vector 4, 4 is the same as the direction vector 1, 1, 2, 2, 3, 3, 4, 4, 5, 5? They'd all be equivalent. It's just multiples of each other. So if I got this direction vector 4, 4, I could leave that. I could say my equation of my line is any one of those points. Doesn't matter if you pick A or B. So let's say I picked A, 1, 4, plus T. And I could write 4, 4, or I could write 1, 1. You could write pi, pi. I don't know if I'd recommend pi, pi. E, oh. No, 0, 0 does not work. Right? Always. Michael will always find a way. The imaginary number, okay. Aye. Pirates like that one. So our parametric, did they ask for parametric and Cartesian? Yeah, they did. This is, you know what? You will like this because it's like, this is not hard, and I have to give you more marks every time I ask you for stuff like this. So it's a good thing that way. X equals 1 plus 4t. And y is equal to 4 plus 4t. 4t. There we go. Ooh, I'll give you guys a math later. Math puzzle. So then the Cartesian, we would get t by itself. So this first one is x minus 1 over 4 equals t. And the second one is y minus 4 over 4 equals t. So I think this is a great example of where those that don't understand cross-multiplying are maybe a little bit of a disadvantage. Because the whole idea of cross-multiplying was I'll multiply both sides by 4 and then both sides by the other 4. Can you see that you don't need to do that twice in this equation? If you multiply both sides by 4, you just get x minus 1 equals y minus 4. Much easier than having bigger numbers. And rearranging this equation, you would get y equals x plus 3. Can you see that if you had used 1, 1 instead of 4, 4, you would have got that equation right away? Or had you used I, you could multiply everything by I. The definition of the imaginary number I. The answer is yes. We could. I've been toying around. I think we'll finish vectors and have our test and have a couple lessons. So I was like, should we do some conics, complex numbers? You don't like conics? Oh, you don't know what that is? Okay. A lesson on 26. Okay. So now we're thinking in 3 dimensions. We've got a point P. We've got a point Q. There is some line that goes through those points in 3 dimensions, and we want to find the equation of that line. Well, What do we need for an equation of line? We need our direction vector. Our direction vector B, okay, somewhere there would be an origin. Can you see that if I wanted to go from P to Q, I could do that by first going from P to O and then O to Q. P to O will be negative 1, 5, 3. And then O to Q will be 2, 0, negative 4. So I find that if you think too hard about your direction vector, you're like, I can't remember how to find it. But if you draw the diagram, it's really easy. And then our direction vector in this case, negative 1 plus 2 will be 1. Negative 5 plus 0, negative 5. And negative 3 plus negative 4, negative 7. And so our equation of our vector equation of line will be take one of the points. I always pick the first one. I don't know why. Plus some scalar t times the direction vector. And you've got your direction, your vector equation of the line. Yes. Just for fun, let's put it into parametric. You always have to do parametric first before you go Cartesian. Parametric would say that your x value is 1 plus t, your y value is 5 minus 5t, and your z value is 3 minus 7t. For your Cartesian, solving for t, can you see that t is equal to x minus 1, t is equal to y minus 5 divided by negative 5, and t is equal to z minus 3 over minus 7. So the Cartesian form of this equation is that x minus 1 equals y minus 5 over negative 5 is equal to z minus 3 over negative 7. And you get an equation equating three of them all together. Not exactly what you wanted. No. But that would be the Cartesian form of this one. Hence, why we don't have a very good way of doing, like, it's not like, oh, in grade 10 you learned y equals mx plus b. That's why we didn't learn some crazy nice equation for 3 dimensions in grade 11, because it doesn't work very nice. Okay? But from this, right, when x is 0, okay, can you see that y has to be 10? When x is 0, y has to be 10. And when x is 0, z would have to be also 10. Okay? So when x is 0, y is 10, z is 10, is a point on this line. However, it's probably much easier to see that, oh, if I want x to be 0, what should t be? Negative 1. And what's 5 plus 5? 10. What's 3 plus 7? 10. And it works out. You can find any point in 3 dimensions so easily from your vector equation line by just randomly picking different values of t. If you want to use the Cartesian plane formula, you have to randomly pick a value of x and do a whole bunch of calculations to find out what would the corresponding y and z be that would work. Okay, you could do that as well. Okay, so then the next question says, does the point negative 1, 3, 5 lie on the line? And the easiest way to figure this out is to use the parametric equations. So our parametric equations were, so for example, if your x value is minus 1, your parametric equation here said that x is equal to 1 plus t. Your parametric equation for y, and now we'd plug in 3 for y, our parametric equation for y was 5 minus 5t. And our parametric equation for z was 3 minus 7t. I'm just going to draw an arrow off of this one. A little bit of mental math. Can you see that if you solve this equation, t would equal negative 2? If you solve this equation, move the 5 over, I would get negative 2. Divide by negative 5, I would get t equals negative 2/5. And if I solve this equation, move the 3 over, divide by negative 7, t would equal negative 2/7. In order for the point negative 1, 3, and 5 to be on the line, all of those t values would have to be the same. Because you need to be able to go a certain multiple of your direction vector and be able to stop there. And since the multiple t is different to get to each of those points, this point is not. So I can write, since the t values are different, okay, we'll see if it comes up as SMEC the t values. Oh, oh.
You are lucky that I recognized it.
All right.
It's not fair. It doesn't. I don't think it knows that smack is a word. Like it knows that smack is a word, so it would intentionally try to make something that makes sense.
SMEC. If you want to spell SMEC,
Play since. The first one was play since. The first one was since.
well, you were right. But it did come up with SMEC second. SMEC. SMEC. No. This is a great example of where usually in the English language the CE would make an S sound, but since we are making up a word, we can make it say however we like, which the English language allows.
The English language doesn't allow for a lot of
Right, so this is obviously SMEC, and it is very important. I will definitely include SMEC in the title of this video so that if you ever want to watch it again in the future, you can search SMEC on YouTube and it should come up. Just like a video I made for my grade 9 transitional math about 7 years ago where multiplying by the reciprocal, like dividing by a fraction, you have to multiply by the reciprocal. But for grade 9s in transitional math, multiplying by the reciprocal is hard to remember. So we called it flipski doodles. And if you search up flipski doodles on YouTube, I am the only one who has ever titled that in a YouTube video.
especially about math.
What?
How do they spell it?
SMEC.
No, we're SMCE.
Yeah.
That's not SMEC. That's SMEC. That's like, that's Yeah, it's definitely from Czech Republic or something. Okay. Okay, we just found a point that doesn't lie on our line. So there's another question. Does this point lie on the line? No. All right. 1 plus t, 5 minus 5t, and 3 minus 7t, negative 5, and 5. So again, using the parametric equations, solve for t. Here, t is equal to 2. Here, move the 5 over, negative 10 divided by 5. T is equal to 2. And finally, move the 3 over, divide by negative 7. T is equal to 2 over negative 7. And I just did a teacher no-no, right? Where you give 2 examples, and usually one example is like in favor and one is in against, so that students would get an example of what it looks like when a point is on the line. But no. No. No, you don't get that luxury. You're going to have to suffer for the first time on your quiz to be able to tell. Oh, no. I mean, if t is 2, it's not like this would be hard for me to actually figure out, right? You're like, oh, maybe the mathematics was too difficult for Mr. JR to make an example that worked. If t is 2, right, we'd have 3, negative 5, negative 11. And then it would work. But I really like this example because it doesn't work. And it goes against what? We don't have time for another example? Oh. All right, we'll end here.